Did you know that Newton's law of cooling is used all around us? Well, I wanted to conduct an experiment that would help compare the theoretical data of Newton's law of cooling against the actual data collected. And I originally thought that I would do something with forensics, time of death. But since I don't have bodies to work with, I thought, okay, I'll do it with tap water. So what I did is I took the hottest tap water that I could get out of the kitchen sink, which was 117 degrees Fahrenheit, which equals 47.2 degrees Celsius. I then placed the water in the freezer, which is kept at 2 degrees Fahrenheit. My refrigerator actually has a display of actual temperature in the freezer, so I was able to maintain and verify that I was able to maintain that temperature in the freezer. I measured the temperature every 5 minutes for the first 30 minutes, and then I took an additional reading after a total of 2 hours. And in between each of my measurements, or right before each of my measurements, I actually shook the bottle a little bit to verify or to make sure that the water inside of the container had at least a fairly consistent temperature throughout, so that the edges of the water wouldn't be cooler than the inside of the water and so forth. So I had to make sure and do that. I had taken a reading at 5 minutes, but I really wanted to use a 10-minute reading for my calculations of theoretical data. So to recap, my initial temperature of water was 47.2 degrees Celsius. The temperature of the freezer was maintained at a negative 16.7 degrees Celsius, which is 2 degrees Fahrenheit. Now let's take a look at Newton's law of cooling, which we take time and temperature into account, and we need to calculate our value for K. So after 10 minutes, I took a reading of 106.0 degrees Fahrenheit, which equaled 41.1 degrees Celsius. You'll notice that time is at 10 minutes, and if I plug in the values of starting temperature of the water and the freezer, it's a simple it's simply mathematics at that point, calculating the value of K. So what I was able to do was just go through the mathematical process. Now notice that I've got a negative 10K in my exponent. Well, the easiest way to get rid of that is to take the reciprocal of both sides to remove the negative from the exponent. And that basically, from there, I can calculate K to be 0.0101 per minute. We are dealing in minutes here. Now that I've got that K, and I've got my starting temperature of the water in the freezer, now I'm able to go back and plug those values in to Newton's law. So what I did is I wanted to find out what would happen after 120 minutes. So I simply used that calculation again, and I'm trying to find T120 here. So notice that I have negative 0.010 in for my K, and I again simply put these values back into the equation and apply mathematics. Okay, so applying mathematics, I found that the theoretical temperature after 120 minutes, 2 hours, was to be 2.317 degrees Celsius. However, and I went ahead and I graphed this equation in MATLAB, and then I plotted my points as well, showing approximately how my results came up against the theoretical results. Now, I did come up with 1.33 repeating degrees after 120 minutes. Now, the initial temperature and the temperature after 10 minutes were used to calculate the value of K. Now, some of the problems that could exist are that maybe my reading after 10 minutes wasn't exactly correct. Maybe I didn't shake the water well enough. There could be a lot of variables here. So determining which is more accurate, the theoretical or the actual, it's hard to say. What would happen if my reading were just a little bit off? What if I would have taken that calculation to, 8 decimal places instead of 3 or 4 or what have you? So it's hard to say what is more accurate than the other, the theoretical or the actual, but I think regardless, we are always going to come up with a variance between the two.